In this video, we're going to determine whether the following parametric curve has either a horizontal tangent, a vertical tangent, or neither at a specific value of the parameter when t equals 1. So we're given this following parametric curve, the x-coordinate as a function of the parameter t, and the y-coordinate as a function of the parameter t. Before we dive into any specifics, I just want to remind us of what we're thinking about in terms of slope for horizontal tangents, vertical tangents, and those types of ideas. So first, if we're thinking about horizontal tangents, we can think back to what we know from Calculus A. A horizontal tangent basically occurs when the slope is equal to 0, or the slope is flat. Okay? So if we're thinking about slope, we're still thinking about dy dx, and we want that to be equal to 0. But dy dx for a parametric curve, we write in terms of, well, dy dt, the derivative of our y-coordinate with respect to the parameter, all over dx dt, the derivative of our x-coordinate with respect to the parameter. So if we want a horizontal tangent, what that means is dy dt over dx dt, since that's the slope, we want that to be equal to 0. In a more practical sense of what that means is we need that numerator dy dt to equal 0, and we don't want that denominator to equal 0. So if we have 0 over a number that's not 0, we're guaranteed that's 0 basically. On the other hand, if we're thinking about a vertical tangent, basically what that means in this case is rather than a slope of 0 or where the slope is flat, we want a slope that is directly up or down. So the slope in this case, we're thinking really looks like either plus or minus infinity. So if we cast this back in terms of dy dx and what we know about parametric curves, what that means is we want dy dt over dx dt. Since that's the slope, we want that quantity to approach plus or minus infinity, basically signaling, hey, we have a vertical tangent. The vertical or the tangent line is straight up or down. So in order to achieve that, in this case, we want the denominator really to look like 0, whereas the numerator in this case, we want not to equal to 0. So basically, we know when the horizontal tangent, we want that slope to equal 0, dy dx is 0. For a vertical tangent, we want that slope to look like plus or minus infinity. Now you might be asking, well, in both cases, we wanted either numerator to be 0, denominator 0, and the opposite to, or the other one not to equal 0. What if they're both equal to 0 though? So if they're both equal to 0, dx dt 0 and dy dt 0 for a specific t value, what we really do then is take the limit as t approaches that specific t value of the slope and see what happens. We do a little more investigative work with our limits and our slope. All right, let's get back to the problem at hand though. We're given some parametric curve, x as a function of the parameter, y as a function of the parameter, and we want to know if this specific parametric curve has a horizontal tangent, vertical tangent, or neither, when the parameter is equal to 1. So what we should do in this case is think about two cases. Basically look at, well, what happens for dy dt and what happens for dx dt. So what I suggest doing in this case, computing each of those derivatives separately. So dy dt, calculate that derivative, and then see what happens at that specific t value we care about. In this case, t equals 1, or when the parameter is 1. So let's take a look at the derivative of y with respect to t. So differentiating that y equation with respect to t, we'll get a 4 over 4t times t to the third when we do power rule. Next, when we do power rule, we'll get another factor of 3 coming down, subtracting 1 off that power. We get 3 times t squared. The next term, we have that 23 over 2, all times 2 times t to the 2 minus 1, or t to the first, or just a t, minus 15, and then the derivative of a constant is just 0. So derivative of 17, that's just 0. All right, let's just do a little bit of arithmetic. So 4 over 4 just gives us 1, so we get a leading t cubed term. Then we get minus 9t squared. Then we get plus, the 2's cancel out. So we just get a plus 23 times t. And then we get a minus 15. All right, remember, what we care about is what happens when t is 1. So let's see what happens when t is 1. So let's plug t equals 1 into both sides of this equation. So just substituting a 1 anywhere there's a t. So we get 1 cubed minus 9 times 1 squared plus 23 times 1 minus 15. So we get a 1 minus 9 plus 23 minus 15. And well, if we do all of that arithmetic right, this gives us a 0. So again, going back towards our slope, what that looks like is our dy dt is 0, but we also need to make sure that at this same t value, that denominator dx dt is not 0. So the next thing we do, let's go ahead and check that denominator. So we'll compute dx dt and see what happens when t equals 1. All right, so taking now the x equation, sine of t minus 1 minus the quantity t minus 1 times cosine of t minus 1. Let's take its derivative. So derivative of sine is a cosine times t minus 1. And derivative of the inside through chain rule, that just gives us a 1. All right. Next, we have a t minus 1 times cosine of t minus 1. So we have a function t minus 1 times a cosine of t minus 1, another function. We get to do product rule. So let's go ahead and do product rule on that second piece. So taking the derivative of t minus 1 first, derivative of t minus 1, that just gives us a 1. So we have minus the cosine of t minus 1. Next, we'll do the opposite. We'll leave the minus t minus 1 term all by itself, and then differentiate that cosine of t minus 1. The derivative of cosine is a minus sign, so we'll get a minus 1 times sine of t minus 1. And well, the derivative then of t minus 1, what's inside is just a 1. All right, so let's reduce this dx dt equation a bit. So dx dt is cosine of t minus 1 minus cosine of t minus 1 minus, well, we have a minus, so that actually becomes a plus. And then we have the quantity t minus 1 all times sine of t minus 1. All right, well, let's see. These cosine of t minus 1s, they cancel each other out. So our dx dt, what that looks like is just a t minus 1 all times sine of t minus 1. And again, we care about evaluating dx dt at the same t value. So let's go ahead and evaluate that at t is 1. And well, when we go ahead and evaluate that, we get a 1 minus 1, so you can see where this is going, times the sine of 1 minus 1. So actually what we have is, well, we have a 0 from that first term. And then we also have a sine of 0, which, well, 0 is 0, sine of 0 is 0. So this thing is also equal to 0. So what that means is, not only do we have dx dt is, or dy dt is 0, we also have dx dt is 0. So that puts us into this fun case number 3. Both dx dt and dy dt are 0. So let's see what happens as t approaches that value. So what that means is, we get to take a limit. And what this limit will be, we have a limit as t approaches that value we care about, in this case, the 1, and we take the limit of our dy dx, or our slope. Put this another way, we take the limit as t approaches 1 of our dy dt over dx dt formula, since that's equal to the slope. Another way, we already have what dy dt and dx dt are. So if we go back and remind ourselves, well, on this current page, you can kind of see dx dt, before we evaluated it, was equal to t minus 1 times sine of t minus 1. So that dx dt we can put in the numerator, or the denominator, excuse me. So again, taking what we have for dx dt from before, we're going to put that in the denominator here. So that would be a t minus 1 times a sine of t minus 1. And well, we need to figure out what dy dt is, and we computed that earlier. So let's go grab dy dt. dy dt was this t cubed minus 9t squared plus 23t minus 15. Again, before we evaluated it at 1. So let's go put that in the numerator of this slope. So again, basically what we did before, we already saw that the numerator and denominator, they both look like 0 in this case as t approaches 1, because we literally just evaluated those things from before. So just to remind ourselves, this numerator from before, this thing looked like 0 when t was near 1. And this denominator, when we plugged in t as 1, this thing also looked like 0 as well. So this looks like a 0 over 0 limit, which means we get to do some L'Hopital's. So since dy dt and dx dt were both 0, when we approached 1 or evaluated those derivatives at 1, we know we're going to be able to do a L'Hopital's because we have a 0 over 0 type limit. So let's go ahead and take the derivative of the numerator, derivative of the denominator separately, and basically see what happens in this resulting limit. All right, so the derivative of the numerator, we have a 3t squared, doing power rule, minus 18 times t, and then plus 23. Taking a derivative of the denominator, well, we have a t minus 1 times a sine of t minus 1. So we have a product of two functions. We get to do product rule. So taking a derivative of the t minus 1 just gives us a 1. So we have 1 times sine of t minus 1. Then taking a derivative of the second term, so again, we add to it the first function, the t minus 1, differentiating that sine now of t minus 1 gives us a cosine of t minus 1. All right, let's see what happens as t approaches 1 in this case. So we plug in a 1. Let's do a little thought experiment. So plugging in a 1 here, we will get a 3. We'll have minus 18, and we'll have plus 23. So if my math is correct here, basically what that will give us is a minus 15 plus 23. This thing adds to 8 in the numerator. So overall, this numerator, oops, going the wrong way here. This numerator does not look like 0. This denominator, let's see what happens. Again, as t approaches 1, in this denominator, we get a 1 times a sine of 0. Sine of 0 is 0. So this first term altogether is 0. This second term, t minus 1, that looks like 0 when we have a t equals 1, times a cosine of t minus 1, that's cosine of 0, which is 1. So the second term, this thing also looks like 0. So this denominator overall looks like a 0. So what that means for us, this slope looks like it's heading towards plus or minus infinity, really depending on the signs of everything here. And well, since the numerator is equal to a positive 8, this whole limit looks like it's approaching a positive infinity. So what that means for us is since the slope looks like plus or minus infinity, this answer is this at t equals 1 is a vertical tangent. So again, going through this process, we knew that the slope of a parametric curve, if we go all the way back, is the change of y over the change in x, or dy dt over dx dt. And depending on which one is 0, we either get a slope of 0 when the numerator dy dt is 0 and denominator is not 0, like this case, or we get a vertical tangent when the slope looks like plus or minus infinity, where the numerator is not equal to 0, but that denominator looks a whole lot like 0. And in this case, when we first looked to see what happens at that point of interest, or the t-value of 1, it looked like both the numerator and denominator were 0. So what that allowed us to do is go ahead and take a limit of what happens at our slope as the value we care about, t going towards 1, of both dy dt over dx dt.